Descriptive statistics are used as a means to understand the basic shape or distribution of your data. And in the most basic form, we can look at the measures of central tendency, which include mode, median, and mean. These measures are used to understand the middle of your data set or the middle of your distribution of values or categories. Mode is our first measure of central tendency, and it is used to identify the most frequent value or category in your data set. Next, we have the mean, which is also known as the average or the arithmetic mean. And this is essentially the sum of all of the values in your data set divided by the number of values. And if you're looking at a population or a sample, it's the same calculation. However, a population is identified using what is known as mu, whereas the sample is identified with what is known as x bar. The one issue with the mean is that it can be influenced quite heavily by any outliers that are in your data set. So an outlier is essentially a value that is extremely low or extremely high within your greater data set. Similarly, the median can be used to also identify the middle of your data set. But the difference is that you're taking all of your values in the data set, rank ordering them, and then finding the middle value. So there's two different cases of your median calculation. The first is if you have an odd number of values in your data set. If you have an odd number, you'll simply take the middle value in the rank order. If you have an even number of values in your data set, you'll take the two middle numbers, add them together, and divide by 2 to take an average of the two middle values. The good thing about a median is that it's not influenced by any outliers. That's because with the median, you are rank ordering your data set and just taking the middle value. So if you have 11 numbers in your data set, the middle value is the 6th number. So if you have outliers in your data set, their value itself relative to the other values in the data set really have no bearing on the median. So in terms of the mode, mean, and median, there are some very specific use cases of them. However, generally speaking, they're good to use in combination with each other. Mode is most often used for qualitative data where you have either numbers representing a category or just categories or text-based data, because it's more likely that you'll have multiples of the same category or value. On the other hand, mode is less likely to be used for numeric data that is highly precise, because the more precise your data is, the less likely you'll have duplicates of the same value. Mean and median can be used for different types of distributions, but I would recommend always reporting the mean and median because they tell you different things about the data, and having both of them can tell you more about the distribution. In some cases, presenting only the mean or only the median can be very misleading about your data set. A great example of this is reporting the average score on a test or exam. If you just report the mean, it can be misleading where you might have outliers that are either very high or very low, bringing the average up or down. Next, we have the measures of dispersion, which are concerned with the spread of the values within your data set. We can use tools like the range, interquantile range, standard deviation, and coefficient of variation to describe the distribution and the details of the spread of values. The most basic measure of dispersion within your data set is to calculate the range, which is the difference between the maximum value and the minimum value. This can only really be used with numeric values, and it's recommended to be used with interval or ratio data. The next measure of dispersion is called quartiles. And a quartile is when your data is split into 4 segments, and each segment is an equal portion of your data set. It's important to note that quartiles is specific to dividing your data into 4 portions, but you can also do this with 5 portions or 10 portions, etc., but they are called different things. So a quartile is for 4 portions, quintiles is 5, deciles is 10, and so on. Specific to a quartile, so 4 portions, is the interquartile range. So this is the difference between the lower 25th percentile value in your data set and the upper 75th percentile value in your data set. The interquartile range is thus the middle 50% of your data set. The next measure of dispersion is called the standard deviation. And this measure is the most common measure of variability or dispersion of values within your data set. The standard deviation calculation outputs a value that is directly related to your data set and tells you the distribution of data within your distribution. So in this picture of a normal distribution, you can see that there is 68% of all data values within 1 standard deviation of the mean. If you look at 2 standard deviations from the mean, you can see that there is 95% of all of your data values. And at 3 standard deviations from the mean, you can see 99.7% of all of your data values within the data set are within 3 standard deviations. The formula used to calculate standard deviation does change between looking at a population and looking at a sample. When you're looking at a sample of a population, the denominator is n-1. And this n-1 is used to remove the bias of looking at a sample versus looking at the total population. When your data set is large, your difference of standard deviation between the population and sample calculations will be fairly small and somewhat insignificant. And as your population and sample grows in the number of values present in the data set, your difference between the standard deviation of your population and sample calculation will diminish and be negligible. When your sample size is really small, so under 30 samples or observations, the n-1 in the denominator of your sample value will have a much more significant impact on your standard deviation result. So once you've calculated your standard deviation, you can get an idea of the spread of your data. If you have a low standard deviation, it indicates that the data is very close to the mean. So most of the values are very close in value to your average data value. If your standard deviation is very high, that means the spread of your data is very large. So not many of your data values are going to be close to the mean value. Now, of course, the standard deviation is not comparable to other data sets because it's very specific to the data that you're looking at. So your standard deviation, you have to then compare to the mean of your data set to get an idea of the spread of the data. You can't simply look at the standard deviation alone and determine if it's a low or high value. It's very dependent on the average value or the mean value of your specific data set. Next, there's what's known as the variance of your data set, which is calculated by squaring the standard deviation. I just wanted to mention that this is a measure of dispersion, but it's really rarely used, and it's rarely used because it's so difficult to interpret. So when you're looking at the variance of your data set, it's difficult to interpret anything because the value is going to be much larger than your standard deviation, and thus relative to your mean value, it has very little meaning. On the other hand, a coefficient of variation can be helpful to compare different data sets with each other. So the coefficient of variation is essentially a standardized measure of dispersion where you can then compare it to other coefficients of variation without worrying about the actual values seen in each data set. The calculation itself for population and sample sizes is the exact same. It just uses different symbology to identify each value. Lastly, we can look at the measures of shape or relative position of your distribution. So first is the skewness of your data set, which measures the degree of symmetry within your data set. So you've probably heard of what is known as a normal distribution, and that's when the skewness is neutral, so its distribution is perfectly symmetrical. If your data set is known as left skewed, that means the majority of your data set is on the right side, and you'll have some trailing values or infrequent values on the left side. So it's where the tail of the distribution is that indicates its left or right skewness. So on the other hand, a right skewed distribution will have its tail or least frequent values on the right side of the distribution. So this diagram here is a good illustration of the difference between a normal distribution, a left skewed, and a right skewed distribution. And lastly, kurtosis is used to measure the flatness or peakness of your distribution. So skewness was measuring the lateral distribution of your data, and kurtosis is measuring the height of your data. So as you can see in this diagram, a leptokurtic distribution will have a very high peak, and on the other hand, a platykurtic distribution will be very flat. The kurtosis of your data will tell you the frequency of data around the middle. Skewness of your distribution is discussed often in journal articles. However, the kurtosis of a distribution is much less frequently used, as it's somewhat redundant to talk about the kurtosis when it overlaps in its explanation of the distribution. So there's better measures, as you now know, to measure the dispersion of data. So now I'm going to go through some examples that we discussed in the formal lecture, and I'm going to use R and RStudio to provide those examples. The dataset I'm using for this demo is Trump's tweets from 2014 to 2021 when his account was banned. 2014 was the time he said he was going to run for president, and I just thought this dataset would be kind of funny to look at, since Trump was known for his outspoken tweets. So this is RStudio. This whole program, this application, is known as RStudio. RStudio, if you're not familiar, is used to interact with the R programming language, and RStudio is used to use statistics and spatial statistics as well as other things. This file here, so in this upper left quadrant, this is where you can use your code. In the bottom left, this is where you'll have your console, and the bottom right is you can have different tabs. So this one currently is just showing my files in the folder that's listed here. Then you can have plots that are output into here. You can have packages. You can have a help where it'll tell you about a tool or package, and then the viewer. So I'm going to just put it back to files. Up here, this is an important window here. This is called the environment, and this tells you all of the different data frames as well as lists or variables that you've created in your R session. So this file here is known as a R markdown file, so .rmd. And this is helpful because you can integrate chunks of code with the just general Word document type of thing. So you can have bolded titles, subheadings, you can write paragraphs, and you can also output code and have it integrated directly into a paragraph, for instance. And this will output as different files. So if you go up here, it'll say knit. And if you click this down arrow, you can knit to HTML, PDF, or Word. So if we click the knit to HTML, you'll see down here in the console, it's telling you what is happening in R. And it's basically just saying, we're running your code that you wrote. And it'll output it to an HTML file, as you can see here. So you have like the title that's bolded, as well as my name and the date. And then you have setup, and it'll have the chunks of code, and as well as the outputs, if that is applicable. You can also see here, I've written a sentence, and I've integrated the answer directly in the code, or in the paragraph or sentence rather, using inline code. So this is also inline code as well. And I'll show you how to do that when I go through the tutorial. You can also see it outputs plots. Here's a box plot, etc. So this is a very useful way to show your code, and it is great for doing assignments or doing a report or whatever you're doing. So I'm just going to close this for now. So the first thing I want to talk about is the setup. So what you need to do to get going with your data analysis in R. So R is great because it is free and it's open source. And that means that people will create what are known as packages to do very specific things. So the R programming language was developed, and it can do a range of different functions such as the mean, median, etc. And you can select data, you can interact with your data sets and manipulate it using base R. So base R is just the functions that were written into the R programming language to begin with. However, if you want to do something more than what is in the R programming language as base R, you can download packages from the internet that are free, and you can use them to do more complex things or make your life easier or create nicer looking plots. So the first thing you would do is install your packages. You can go up to here, Tools, Install Packages, and you can type your package in. So say you wanted to download the dplyr package. You would type dplyr, and then it comes up here, and then you click install, and then in the console down here it would come up as installing, and essentially it just goes onto the internet where the file is located or the package is located, download the zip off the internet and install it onto your actual machine so it's ready to use. I already have this package, so I'm not going to download it, but that's how you would do it. You can also write code straight into your file. So if I wanted to install packages through code, you can go up here, you can click where there's an empty white space, and then go up here, click the down arrow, and click R, so it'll insert a new R chunk, as it says. And then it's highlighted with this kind of gray box, and the chunk is delineated by these symbols, basically. You can also create an R chunk by just creating these symbols, and it will know that it's an R chunk. So that's another way to do it. So to install a package, you can go install.packages, and you can see as I'm typing it, it'll come up as a function, and you can just hit the tab button, and then you can put in the package that you want to install. Now, to run this and to install the package, you can either come up here and click this play button, and it will run all of the code that's within this R code chunk, or you can click the line that you're on. So if you just click on the line and then hold Control and hit Enter, that'll run the line of code. Or if it's multiple lines, you can select any of the lines that you want to run and also hit Control Enter, and it'll run the code. So we've already installed the packages, so I'm just going to go ahead and delete that. And the first thing we have to do is, once we've downloaded the packages onto our PC through install packages, we have to actually load the library into the R session. So once you have the package on your computer, when you go to use a script in R doesn't know to use or access that package unless you tell it to. So the first thing you have to do is load libraries. So libraries are just essentially these packages that you've downloaded. So the one package that we're going to need for this is called Tidyverse. Tidyverse is essentially a collection of multiple packages that add greater functionality and more intuitive functions and code that you can look up yourself and kind of get a better idea of what Tidyverse is, but just know that it just makes our life easier when we're writing code. So I'm going to go ahead and click this play button, and it ran it. Right here, if you notice, there is a little green bar that just tells you that it is running that piece of code. And that's useful if you're running a lot of code at once. It'll tell you kind of the progress or what function that it's on or line of code. Down here in your console, you can see that I've run this function, this library function, 4 times. So if you watch down there, I'll click the play button again to run this chunk, and you can see that it shows up in the console. So the next thing we need to do is import the data set into our R session. So right now I'm using what's known as a project in R, and that is essentially just an easier way to contain all of the information we need to use in this script. So we're going to use the read CSV function right here, read underscore CSV, and then a normal bracket, and then a quotation, and you just then write the file name. So the file name is Trump underscore insult underscore tweets underscore 2014 to 2021 dot CSV. So you need to include the file type as well. So this is encapsulated in quotes and then in brackets, and the function is read underscore CSV. This little arrow here, this is essentially an equal sign. So we want to read this CSV file into the R session, and then we're going to want to name this CSV file tweets. So let's go ahead and run that. And you'll see down here in the bottom right, this is the container, the project container or folder with everything we need to run this code. So here is the CSV file right there, and that coincides with this line of code here. So if we run this now, you'll see that this CSV file has now been read into the environment or the R session, and it's now here in the environment. And if you click this little blue and white arrow, it tells you some information about your tweets data frame. So a table is called a data frame in R. It tells you how many observations are in the data set, and there are 5 variables. So how many variables are there? If you go over here and click this little table icon, it'll actually open up the data frame or table in our studio. So now we can see what that data set is actually showing. So you can see the first variable is ID. So this just gives a unique identifier to each individual observation. Each observation also has the date in which Trump actually tweeted this out. This data set also has the target. So Trump is very well known for insulting people, as any normal president would, is insult people on the internet like they're a 5-year-old. And the target in this case is Thomas Frieden, and his insult is categorized as fool, and the original tweet is here as well. And you can see here in these first 2 observations that this tweet here is most likely the same as this tweet. So why are there duplicates in this data set? The reason is that in each tweet, he could have multiple insults or multiple targets. So the person that created this data set went through each tweet and wrote down all of the insults and all of the targets of this tweet. So just keep that in mind going into this tutorial, is that there are multiple duplicates of the same tweet. So we need to account for that when we use the different measures. And because there are multiple duplicates of the same tweet, that also means there could be multiple duplicates of the same target or duplicates of the same tweet date. The other thing is you could also have multiple tweets that are different on the same day. So also keep that in mind. The data set was taken from Kaggle, which is a free source of data sets, and you can get all sorts of interesting data sets. You can get really serious data sets, or you can get just kind of funny data sets like this one. So let's go back to the RMD file tab up here. And so we've run this piece of code, and you'll notice here with this hashtag, so there's a hashtag, $, number sign, whatever you want to call it. And then I have this hashtag, and then I have this sentence here. And you'll notice down here, it shows up as well, but it didn't actually do anything with it. And the reason is, if you use one hashtag inside a chunk of code, it's known as a comment. So any comment in a chunk of code won't be run. It will be known, well, it'll be read as a comment, and thus it won't read or do anything with it. And if we take that away, so if we take this hashtag away, you can see now that the text color has changed, and it's giving us an error here because it's expecting, it doesn't know what this means. It thinks this word right here, this, is a variable, but it doesn't know what it means. So if you go to run this code now, it'll give you an error saying unexpected symbol in this data. So that is important to note. So if we add the hashtag again, then the error goes away and we can run this code again. Another thing is you can run this piece of code again and again, and it will just continually overwrite this variable here. So this data set will just be overwritten. And that's important to know. If you ever mess up your code and you output something and you overwrite something that you didn't want to, it's not a big deal. You can just go back, re-import the data, and then run the code. So moving on, first thing we need to do is clean the data set. So there's not much to do here, but there are a couple things that I want to do. First thing is I want to count the number of characters in each tweet so we can later analyze the length of tweet that Trump will typically use. So the way we do this is by putting in tweets. So this is the data frame, or the table is called tweets. And then we use a $sign to say, okay, in this table called tweets, we want to select this column. So the $sign lets you select a column. And the car underscore count, or character count, but it's just abbreviated, that is the column that I want to choose. But you'll notice that in here, there's no column called car underscore count. But what I'm doing here is creating a new column called car count. And then I'm going to use this little equal sign, which is the less than and then minus symbol. And you don't need to know this, but this is a function called lapply. And it's essentially going to take the tweet column. So it's going to look at this tweet column. So all of these tweets. And it's going to apply the string length function to each row in that column. And that basically will just, if I run it there, you can now see that there's a new column and it has the string or character count of each tweet. And you'll notice this one is good because this is 140 characters. And if you're savvy with Twitter, then you would know that the character count max was 140 for a long time. Okay, so one issue later on, I mean, you don't really need to know this, but I need to change the data type of the character column. So if we look now, you can do type of bracket tweets $, and you can see it'll list out the columns that are available to you, and you can use your arrows up and down to select the one you want and then hit tab, and then it'll write it for you. That's helpful to make sure you're not making any typos. And if I hit Control Enter on that line, it'll give us the type of what this column is. So this column here with all of the character counts is considered a list. And we don't want that. We want a different type of data. So what we need to do is use this function that's called as.double to change this column into double. And then if you run the type of, you can see now it's switched to double. So that's good. That'll just make our life easier later on when we need to use that column. The next thing we want to do is remove any tweet that is greater than 280 characters. In 2017, Twitter upped its character maximum to 280 from 140. So we want to remove any tweets that exceed 280 because there's some sort of error in that tweet, and we don't want it in our data set because it'll affect all of the measures that we will be using. So if we run this, it will just remove, you can see here the observations has changed. So if we go back up to the import data set step and run this chunk again, you can see the observations is 10,360. And then if we rerun this clean data chunk, you can see the observations has changed. So it has filtered out any tweets that are greater than 280 characters. And this is this chunk of code right here is essentially overwriting the tweet's data frame, and you're telling R to use this data frame called tweets, and then this set of symbols is used to pipe the data into the next function that you're using. So you're starting with the tweets data frame, and you're telling R, okay, I want to filter the data, so I want to eliminate any rows that exceed 280 characters. And I want you to look for this column within the tweets data frame. So it's going to be, this is the data frame of tweets. And then I want to look for car count, this column, within this data set or data frame. The filter function is used to manipulate rows in your data frame. And this is, the exclamation mark is essentially saying, don't include these rows. So it's going to look for any row where the character count exceeds 280, and it's going to eliminate with this exclamation mark, it's going to eliminate those rows from the tweets data frame. Okay, So I'm just going to run that, make sure it's run. Okay, moving on. So this is our first example, and it is the mode. So the frequency, the highest frequency of whatever you're looking at. So the first thing we're going to look at is the mode of target. So again, if we look in the data frame, the target lists the person or thing that Trump is tweeting about, the subject of the tweet. So what this is doing, you're taking the tweets, the data frame, you're going to group by the target. So you're going to group by this column. And then you're going to summarize, which creates a new data frame with the number of times that target has come up in a tweet. And then we're going to filter it. So we're only selecting the highest number of times a target has been talked about. And we're going to save this new data frame as target, and then we're going to call it so it comes up in here. So let me just run it. It'll make sense once I run it. So the number one most talked about target in Trump's tweets during this time was the media, and it was talked about or came up in tweets 1,271 times. So it just grouped all of these. So anytime a target is talked about more than once, it's just counting how many times. So you can see here, the target is in both of these times Thomas Frieden, and it just counts. So that would be 2 times. And then it would just keep counting the number of times it comes up. Or here's Macy's was targeted a bunch of times. So here there's 5 of them. That would be 5 times. But it's doing that for the entire data set of 10,000 observations. So his most talked about target is the media, and it was 1,271 times. You can also, in a R Markdown file, create answers directly in a line of text. So outside of this gray area, if you're typing just in the white area, this comes up as just normal text in any sort of word processor that you would use. The difference is that you can do inline code to create an answer directly in your sentence. So let's go up to the knit and knit to HTML. It takes a second as it goes through all the code. And you can see here, this is the line, this is the chunk of code we just ran. And this is the sentence I was talking about. So it says the most frequent target of Trump's tweets during this time was the media, and it's bolded, comma, which was targeted 1,271 times, and that was also bolded. And so if we close this, we can see, took a little bit there, we can see that this is the inline code. So these 2 star or asterisks is the 2 symbols you need to create a bold effect on text. So you put 2 asterisks on either side of text or code, and it will create a bold effect. The inline code itself is this little tilde and then an R to indicate that you're writing R code. And then you're taking the target data frame that we created. So if we look at this data frame, you can see it's just 2 columns where it's the target and the target count, and there's only 1 row or 1 observation. The target is the media. The target count is the 1,271. But since it is a data frame, we can then select the target data frame, put a little $, and then select the target column. So we're just selecting this value right here. And it'll run that code inline and give you this inline code, or the answer, or it's selecting the value you're telling it to select, and it'll output it as the actual value that you've selected. So that's a really handy thing you can do with R Markdown files. So moving on, another example of mode would be to look at the insult that he uses the most. So if we run this, it's the exact same code, it's just for the insult column rather than target. So if we run this code, you can see his number one insult is fake news, no surprise there. And he used that insult 424 times. And again, you can select the answer right here in the inline code. And that's also helpful because you're less prone to making typos that are a result of human error. So if you're letting R type in the value, then you're much less likely to, you won't have a mistake, basically. Okay, let's get into tweet length. So we can use tweet length to or look at the most frequent tweet length. And in some cases, when you take the mode of a numeric value, it can be really useless. But in the case of tweet length, because there's a hard cap or a maximum number of characters you can use, you might have a better result. But your results also might vary person to person. So let's look at this here. Let's run this code. You can see the character count of 280, which is the modern most maximum value of characters in a tweet, was used the most by Trump, and 900 of his tweets have used the maximum number of characters. And that's interesting because from what I've read about Twitter is that most people don't use the maximum number of characters, and it's actually more beneficial to write a concise tweet rather than it is to max out the number of characters. And that makes sense with Trump because Trump typically will ramble on about whatever he's talking about, and he's maxing out the number of characters. So let's keep going and we'll continue on. First thing we need to do is filter the data set. So we need to filter this tweets data set. So we're only looking at unique tweets. So as I talked about before, you can see here in these first two tweets that they're the exact same tweet, and it's because of the target and insult can have multiple values. Thus, you'll have duplicates of the same tweet. But that's okay. We can easily remedy that by creating a new data frame called unique tweets, and it will be set or equal to. First, we will take the tweets data frame, so the one we've been using this whole time, and we'll pipe it into this function called select. Select is used to select specific columns in the data set. So the filter function is used to select rows, and the select function is used to select columns. So we're going to filter, or pipe rather, the tweets data frame into the select function, and we're going to select tweet date, tweet, as well as character count, and then we're going to pipe it into the distinct function. So the distinct function will look for duplicates of observations, and it will eliminate the duplicates by selecting only one of the multiple rows. So if we run all of this, you can now see there is the tweets, which there are 10,000 of them. There's 10,000 observations because there's so many duplicates. And then you can see unique tweets. There's only 5,618 observations. So if we open that up and look at it, now you can see there's no more duplicate tweets. They're all unique tweets. So during this time, he tweeted 5,618 times, which, as you can imagine, is a lot of tweets. So the first thing we can do is look at the average number of characters that he uses for a tweet. So let's go ahead and run this code. We can see the average number of characters that he uses is 189.8 characters per tweet. And we got this value by taking the unique tweets data frame from the step previous to this one. We pipe it into the select function, which has tweet date, tweet, and character count. And then we pipe that into the summarize function, which creates a new data frame. And we want to create a column called mean_car, short for character, and set it equal to the mean or average of the char count column. And then what we want to do is pipe that information or that data frame into the round function and set the mean to 2 decimal places. So digits equals 2, and that will output this. So that tells us that 189.80, but it doesn't show the second zero. But if it was 189.81, it would show that. It is rounded to 2 decimal places. So moving on, we'll take the median, and it's the exact same chunk of code. The only difference is this used the mean function. This one will use the median function. So the median of the character count of each tweet is 173. So the median is actually lower than the mean, which tells us that the data is showing a left skew, or in other words, he has outliers where the tweets are very high character counts. So he tends to probably max out his character count when he can. And getting these data values on their own is helpful, but it can be difficult to understand what is actually happening. So if we look at a histogram, we can understand visually what's going on. So this is a histogram. So this is ggplot. ggplot is a function to create visually appealing plots of all kinds. And it's just more versatile and easier to understand than base_r's plot function. So we're going to take the unique tweets data frame, and that's our main data source. And then this AES is short for aesthetics, and we want to plot the character count column. So we're looking at this column. That's where the data is, the values are coming from. Then you add a plus sign, and then geom_histogram is our next function, and that adds the histogram functionality, or is telling ggplot that you want to plot using a histogram. The bin width equals 10 means that it'll look in intervals of 10 characters and plot a bar for each of those values. So 0 to 10, 10 to 20, 20 to 30, and so on. And then what I did was I added another function called geom_vline, which adds a vertical line to the plot. And the vertical line is the red one. This red one shows our mean character count, and the blue one shows us the median of the character count. So you can see here, interestingly, there are kind of two peaks. It is almost like this mirrored effect. You have one peak kind of midway, and then you have another peak that is far to the right. And you can see the red line is the mean, and the blue line is the median. So that is interesting. Why are there two peaks? Think about it. With Twitter and the character count, think about why would we have two peaks. So moving on is actually, I want to go back. If you're not familiar with a histogram, I should have said that. If you're not familiar with a histogram, on the y-axis, so these values here, is the number of times that character count had been used. And then on the x-axis is the actual character count, the bins. So like the 0 to 10, 10 to 20, 20 to 30. So this is, the y-axis is the frequency of tweets that can be binned in that interval. And then the bar is telling you, the higher the bar is, the more times that character count has been used in a tweet. So if we're moving on to measures of dispersion, the first one we can look at is range. So we're first going to create a new variable called tweet_chars_min, which is the minimum tweet length or character count of a tweet. So let's go ahead and do that. This is the min function, so it just looks into this data frame, $, this column, and it looks for the minimum value in that. And you can see over here in the environment, there's all of these different data frames that we've created and we've looked at. But then down here is a value. And the difference is that these are variables that are equal to one thing, or one, it could be one value, it could be a list, but it's not a matrix, it's not a table, it's not a data frame. So tweet cars min is equal to 11, which means the shortest tweet that Trump has made was only 11 characters. And the maximum, so using the max function, is 280. We kind of already knew that. Not that this is important, but I was curious, what could Trump have possibly tweeted that was only 11 characters? Because that's like ridiculously short. So what I did was I used the unique function, and I looked at unique tweets and then the tweet columns, so the actual physical or the actual written tweet. And I wanted to select using this square bracket. So looking in the unique tweets data frame, we're looking at this column here, the tweet column. And then to select a row, we will look at this unique tweets data frame and then select the character count, because that's where the minimum value was, and look at where the character count column is equal to 11. And note that there's two equal signs there. And that's because this is not going to be equal to a variable. You're actually looking where this value is equal to something that's in the physical data set. So you use two equal signs and set it to 11 because that's our min value. And when we run this unique tweet, you realize, oh, he tweeted witch hunt in all caps with a exclamation mark. And I just thought that was funny. It really has nothing to do with what we're doing. I just thought it was funny. So in order to calculate the range, we're taking the maximum number of characters he used minus the minimum number. So if we run that and then look at what the range is, it's 269. So we took this variable, which is, if we look over in the environment, the max is 280, subtract the minimum variable, which over here again is 11. So it's just doing 280 minus 11, but it's using a variable name, and it's setting range equal to that value. So now we have another range variable over here. That is 269, and we see it down here as well because we wrote the variable name there, and it outputs 269. So that's our range. So next is the interquartile range, which is looking at the 25th percentile value and the 75th percentile value. So we will first pipe unique tweets into the summarize function, which will create a new data frame. And we want to create two columns. One is IQR_25 for the 25th percentile. And we're going to set it equal to quantile function. And we're going to look at the character count column. And we're going to want to look at the 25th percentile. So that's what the quantile function requires this input, which will tell what percentile you want to output. So in this case, 25th. And then we want another column called IQR_75 with the same function, same column, but this time we want to look at the 75th percentile. So we run that. We can then run the variable name, and it outputs this result. So our interquartile range is 135.25 to 273. So that's our interquartile range. And that is the character count of tweets. So 50% of all data or all tweets are within 135 to 273 characters. So next thing we can do is look at a box plot. So this box plot, again, we're using ggplot. The only difference is that we're using geom_boxplot, and labs is used to create labels on your plot. So the box plot tells us the sort of distribution of data, or how much of the data is within the interquartile range. So this bottom line here of the box is the 25th percentile, and this top line of the box is the 75th quartile range. And this middle section here is the median. Now, these lines are called whiskers, and if you have data points that are exceeding these whiskers, it indicates that these are probably outliers within your data set. But because we don't have that, we would assume that there's no outliers in our data set. All right, so moving on to standard deviation, we are going to create this new table called standard tweet count, and we'll pipe unique tweets into the summarize function, and we'll create a new column in the summarize table called standard dev, and set it equal SD, so standard deviation of the character count column. And we can do that, and we can output the standard tweet count. And right here I've added the round function to round this output to to 2 decimal places. So we get 73.77. So if we add that to the mean, we get the upper standard deviation, so 1 standard deviation from the mean in a positive sense. And if we subtract that from the mean, we get the left side of the 1 standard deviation from the mean. And one thing to note about the standard deviation function in R is that it is for a sample. So if we look at the standard deviation function down here, so if you want to ever look up a function in R, what you can do is write question mark and then the name of the function, so SD in this case. And if you select that and run it with Control Enter in this case, you can see down here it'll give you the information about standard deviation. And right here in the details section, it says, like var, this uses denominator n-1. So if you remember back to the lectures, you would know that the sample calculation for standard deviation is using a denominator of n-1. So in this case, it's fine, doesn't matter, but it's something to keep in mind in the future. So now if we're moving on to the coefficient of variation, you can see we're going to create a new variable called COV, set it equal to with that symbol, the standard deviation of unique tweets, $sign to select the char count column, and we're going to divide the standard deviation of char count by the mean of the char count. So we're going to divide that, and once we do that, it returns a value of 0.388 or 0.39. And that as a value on its own is kind of meaningless because we aren't comparing different distributions. So on its own, it's kind of useless, but that's how you do it. Now, if we look at the histogram again, we can overlay the standard deviation onto it to get a better idea of what it means in the context of our data. Because generally speaking, it is easier to visualize data than to understand what the numbers mean. So if we run this, again, ggplot is the function to plot anything in the tidyverse package. We're inputting the unique tweets data frame. The aesthetics are where you identify the column you want to use for the data. And then we're going to add the geom histogram to make a histogram. We're going to use a bin width of 10 characters. So that's what this is. And then we're going to add the geom v-line for the mean, for the median, for the lower standard deviation, and for the upper standard deviation. So as we had before, the red line is showing the mean of character count. The blue line is the median character count. And the 2 black lines are the lower and upper standard deviation. So you can see that 1 standard deviation away from the mean is all of this information here. And 1 standard deviation will hold 68% of the data values in your distribution. So that's what that looks like. Probably a little easier to understand than simply looking at the standard deviation of 73.77. So now to go back to that question I asked before when you're looking at the histogram, why are there kind of 2 identical distributions in this greater distribution? So why is there a big peak here and why is there a big peak here? there's obviously some reason that there's a peak at about 140 characters and then another one at about 280 characters. The reason for this is that in November of 2017, Twitter increased its character count limit from 140 characters to 280 characters. So with that context, it would be interesting to now look at those two time periods separate from each other so we can compare and see if Trump is maxing out his character count each time he tweets. So before November 7th, 2017, was he maxing out his character count on his tweets? And then similarly, after November 7th, 2017, was he maxing it out by hitting the 280 character count? So in order to separate our data into two different data sets so we can compare them, we need to create two data frames using the filter function. So the first thing we'll do is create a new data frame called tweets_140, which will house all of the tweets that were from November 6th, 2017 and before. And we'll create another data frame called tweets_280 and set that to all tweets after Twitter changed its character max from 140 to 280. So we can do this by writing out tweets_140, set it to with that symbol, and we'll input unique tweets and pipe it into the filter command, and we'll set the tweet_date column to less than the November 7th, 2017 date that's found in the unique tweets. So in here, this is the date format. And as a secondary assurance, we will also pipe this data into a second filter command or function where we'll make sure that the character count is less than or equal to 140, just to make sure that there's no errors in the way we've selected these tweets. So none of them are exceeding that 140 character count. Now with the tweets_280, it's the exact same code, except there's one difference in the way we're actually doing this. And in the first example, we used the filter function and we piped that data into another filter function. But we can actually just use one filter function for both of those commands or arguments. So we can use the tweets_280, set it equal to unique tweets, and pipe this into the filter function where we're selecting the tweet_date column, and it's going to be greater than or equal to this November 7th, 2017 date. And then we use this and symbol to then say only select rows where the character count is less than or equal to 280. So this little and symbol is the way that you can link together multiple arguments. If you wanted to select rows where it's the tweet date or the character date, you can use a pipe symbol like that. It's a little confusing because that's also called a pipe, but that's just the way it is. But the and makes sure that you're meeting this requirement and this requirement. So let's go ahead and run this code. And now we have the tweets_140 and the tweets_280. You can see these two tables have different number of observations now, but they contain the same columns and information that was found in the original unique tweets dataset. So you can see here, they're the exact same columns, but they are different time periods. All right, so moving on, we will now look at the mean of these now 3 data sets. So we have the tweets that max out at 140 characters, then the tweets that can max out at 280 characters, and then we have our original data set with all of the tweets for the entire time period. So I'm not going to go through the code, I'm just going to run it. So when we run it, we can now see that we have the original mean, which was 189.8. We have for the rule change was 128.73, so it's lower, of course. And for the 280, it's 221. So one thing to note about the tweets where they can max out at 280, they can also still be, 1 character long if they want to be. It's just that they can now be up to 280. Whereas the tweets that are maxed out at 140, they can be anywhere from 1 character to 140 characters. So you can see the mean has changed quite a bit between these 2 different ones, as well as this original value. So it's very important, especially with a data set like this, that you understand the context of your data. If you didn't know that Twitter changed its max character count somewhere in between the data, you would have no idea why this data was showing this. So now if we're looking at the median, we go ahead and run this code block. You can see the original median was 173. For the 140, it's 137. So most tweets are maxing out the character count. And for the 280, it is 261. So it's also almost maxing out the character count. Now, if we look at our histograms, you can see with all of the tweets, you can see the blue is median, red is mean. So you can see this is kind of, it doesn't really give you much information because of the max count or the max character count being changed. Whereas now if you look at the only tweets that can be maximum 140 characters, it paints a very different picture. That Trump, when he tweets, is almost always maxing out his character count. He's in a lot of times just rambling on about whatever he's talking about, and he's maxing the values out. When it's at 280 characters, the mean is much lower than the median, which tells us that he tweets probably a lot, and he does still tweet out things that are shorter, but the median or middle of the data set in rank order is very close to the maximum of 280 characters. So if we move on and we're looking now at range, this is not very surprising. You can, I will say for code-wise, you can use the paste function to put together both text and also variables or outputs from your functions. So paste just puts together this text with this output from here. So for all of the data, the range is 269. The 140 category is 107, and the 280 category is also 269. It's nothing surprising there. So now if we look at the interquartile range, we can see that the original interquartile range was 135 to 273, and the 140 is 126 to 139. So 50% of all of his tweets are within 126 characters long and 139. That is almost maxing out his character count most of the time. And in the 280 category, we see an interquartile range of 176 to 277. So it's a little bit more lenient in this category, but it is still very high. Now, if we look at a box plot, we can see that this is our original box plot where it's not really telling you that much. It's a little too noisy. But if we look at the 140 character limit, we can see the median is very close to the maximum. We can see the 25th percentile is also very high, and you can see all of these dots representing outliers in the data. So all of these dots represent tweets that are uncharacterizably small. Their character count is much smaller or much fewer characters than the average tweet. So you can see in this box plot that most of the time he's tweeting, he is maxing out his character count. In the 280 character limit, you see only a few outliers in here, and he tweets mostly at the maximum, but he kind of varies quite a bit in this. Now, if we look at the standard deviation, you can see the original standard deviation was 73. In the standard deviation for 140 character count, you can see it's much smaller. And this is not surprising, because if you're only going up to 140, then your standard deviation is obviously going to be much smaller. And when it's a larger maximum value of 280, the standard deviation can be larger. The coefficient of variation in the first example was kind of useless because it was just on its own, and it's a measure to compare to other coefficient of variations. So you can see here it's actually much more interesting. So for all of the data, the coefficient of variation was 0.39. When we're looking at only tweets that max out at 140, the coefficient of variation is 0.14, which means that in this case, the character count of tweets is on average much more similar in value to the mean than in the entire data set, which again makes sense. And the times where he can max out at 280 characters, the coefficient of variation is 0.33, which means it's a little bit less spread out than with all of the data, which again makes sense, but it is still twice as large as the time where he could only tweet out up to 140 characters. Now, if we look at the histograms again with the inclusion of the standard deviation, we can see that all tweets, this was what we came out with, where the standard deviation, which was very wide in this case because of the way the distribution is shown. And if we look at the 140 character limit, you can see that the standard deviation encapsulates that upper segment of the data. And when we're looking at the 280 character limit, you can see it's a much larger range of character values. And in both cases here, you can see that the upper standard deviation is outside of the bounds of the max character count. And that speaks to standard deviation's inability to work with skewed data. So it's not as helpful to look at standard deviation when you're not looking at normally distributed data, but it can still be helpful. Now, if we're looking at the interquartile range, so this is the all tweets, you can see the interquartile range, so the middle 50%. So this is the lower 25th percentile, And this is the upper 75th percentile value. And you can see, obviously, with all tweets, the values range basically from the max value of 140 essentially to the max value of 280, or very close to that. If we're looking at the 140 character limit, you can see the interquartile range here, shown in black, is very narrow, and that speaks to the fact that he's almost always maxing out that character count. And then again, in the tweets where he had up to 280 characters, the interquartile range is much wider because he has more range, or he has the ability to make his tweets shorter or longer, so that range is a lot larger as well. So that pretty much sums up all of the theory that we talked about in the lecture content, and hopefully it gives you an idea of the kind of visual impact of what these functions mean in the greater scheme of your research, and how also to calculate these things in R and RStudio. Obviously, this isn't a comprehensive guide of how to use R. I would suggest strongly that you look up how to use Tidyverse, which is the package that we used for this, and specifically the dplyr package, which is spelled DPLYR. But that wraps it up. I hope this was at least somewhat interesting or funny, or I don't know what you got out of it, but it did showcase all of the different concepts that we talked about in the lecture.